Lyapunov theory concepts and some basic definitions as well as some direct theorems and all that, and so one or two examples. Now we will continue the discussion further and see some of the further concepts in Lyapunov theory here. Now, one of the things that we saw there in this Lyapunov theory in the previous lecture is, the major issues being two. One is how do you see that, how do you find a Lyapunov function which will do the job for you, and the second issue is like if I have negative semi-definite, what do I do with that? Okay, because many times it is nice to see negative definiteness so that I can conclude more than what I otherwise can conclude. So, we will try to address some of these issues and then try to see further concepts and things like that. So, first issue is construction of Lyapunov functions. So, in some problems it is possible to construct Lyapunov functions following some sort of procedure and all that actually. So, that some of these results we will see here in this particular lecture first. So, one method is something called variable gradient method. Okay. And that because see why this important, because in Lyapunov function analysis, these are what we saw in the last class, all the theorems happens to be like sufficiency condition. That means, if I am lucky I will keep on trying, and if I am lucky one time then probably I will get the results that I want, but in general there is no guarantee actually. Okay. So, how many times I will try? So, instead of doing that, is there any standard procedure to see some of these construction of Lyapunov functions other than the very standard thing that we discussed? See, this x transpose x and all that, the quadratic function may not work out always actually, but that is a standard function that we can try out, and this kinetic energy plus potential energy, that is another function that we can always try out. Okay. But other than that, suppose these two also fail, these two regular candidates fail, then what are the other things that we are worried about actually. So, this is where we lead to this construction concepts and all that. Then first method which comes to picture is variable gradient method. So, this variable gradient method tells us that okay, let us not worry about selecting a v, but let us select a delta v instead. That means, we will select some sort of a gradient of v. Let us talk about that actually, because remember v dot is del v by del x transpose into f of x. So, instead of selecting a v and then working out this del v by del x, because del v by del x is something that will go to picture, right. If I see this previous class, somewhere we discussed about that actually. Okay. Yeah, this v dot is del v by del x transpose x dot. So, del v by del x into f of x, that is ultimately v dot. So, if I have to conclude something about v dot, then why starting with v and then working out this del v by del x and all that, because we know f of x already. If we know f of x, then I will be smart enough to select this v of x del v by del x and see whether my v whatever v I will compute from there, whether this v will satisfy this or not. Right, that is the whole idea actually. Instead of starting with v and then carrying out this algebra, I will just see that what is my f of x and select this del v by del x, and then but remember I have selected only del v by del x. These two 1 and 2 condition has to be satisfied. So, that means, I will solve this del v by del x expression and then get v of x and see whether this v of x satisfies that or not actually. So, it is kind of a little bit reverse idea sort of thing. So, that is what that is the variable gradient method talks about. So, let us select a del v by del x g of x, okay, that contains some adjustable parameters. Okay, then we have to obviously adjust that depending on our f of x, whatever f of x we have actually. Then this expression tells me that this del v is nothing but del v by del x transpose del x, but remember this expression is some sort of a, then this dx contains many components of x actually. Dx is a vector quantity, okay. dv is a scalar quantity. So, if I really have to solve for Vx, I have to be doing, I have to do this integration slightly carefully actually. But nevertheless, if you start with this expression dv is that, so integrate both sides from 0 to x, and then it will turn out that this left hand side is v of x minus v of 0, and then most of the time v of 0 is 0 anyway. So, that is what we will select actually, so sort of thing. And so, this expression will give us that what is my v of x actually. Okay, so, v of x is integral of this gradient, but this integration that we are talking about has to be done component wise actually. We will see some procedure and all that further when you go along actually. And also remember that this del v by del x what you are selecting, this g of x, it must satisfy so called Corl condition actually. That means, this if I see this del g I by del x j, it should satisfy this del g j by del x I. So, if I take like G is a vector, remember that. Okay. So, you take any component of that vector and take the partial derivative with respect to any component of state vector, and if you reverse that sequence, that has to be that needs to satisfy. Remember, right? What does that mean? This del G by del x, okay, what you see here, okay, this G is already a vector, remember that. So, if I talk del G by del x, that is actually a matrix, and this matrix has to be symmetric actually. Okay, that's all we are telling here actually. Okay. And also remember, there is another thing, that this integration, okay, this value depends on the initial and final states and not necessarily on the path followed actually. And if that is so, then this integration can be done component wise actually. That means, I travel along x1 axis first, then I will travel along x2 axis, then I will travel along x3 axis, like that actually. So, I do not have to directly radially go from 0 to x, 0 to x that way. I can go in a component wise, x1 first, x2 next, and things like that actually. Okay, that is how I will be able to integrate this actually. So, this is what is done here. So, v of x, when you integrate this, what does that mean? V of x, you first integrate along x1 axis. So, all other axes are 0 anyway, then whatever function comes out, plus wherever you are, that x1 is remains actually. Then now you vary x2, x2 will vary from 0 to x2, then you vary x3, okay, x1, x2 and x3 tilde, that is your variable, this integration variable and all that, and keep on doing that until the last coordinate is reached actually. Okay, so, that is the expression what you see here actually. Okay, so, with the assumption that v of 0 is 0 actually. Okay, v of 0 has to be 0 for that. All right. So, that is that's the way to proceed further actually. So, remember, I have to start with a gradient of Lyapunov function g of x, which will contain adjustable parameters, which I have to adjust later depending on my situation, and this g of x must satisfy some sort of a curl condition. That means, if I take this del g by del x, that becomes a matrix, and that matrix has to be symmetric actually. All right, then only I will get a solution which I want, otherwise I will not actually. Okay, and the procedure to get v of x out of this gradient vector is like that. If I have already got a gradient vector and which will do my job, I know, then I will compute this v of x that way, and then I will go back and see whether those conditions are satisfied or not, that v is positive definite or not essentially. Okay. So, let us see this theorem actually. Okay. So, the function g of x is the gradient of a scalar function v of x if and only if the matrix del g by del x is symmetric. That is what I told you just now, this del g by del x matrix that I told you. This, in other words, this curl condition that we are talking about is nothing but this condition that del g by del x is symmetric, that is all it tells you. Okay. Now, it is a if and only if condition. So, let us see whether that is true or not actually in a way. Very quickly, this is very straightforward thing also. The proof is there in Marquis' book, but I will also take you through here itself actually. Okay. So, del g by del x, when you mean, that is what we mean, del g by del x, del g 1 by del x 1, del g 1 by del x n and all that actually. So, this matrix needs to be symmetric actually. Now, how do you show that if and only if condition? So, first let us see that this is symmetric and all that, it is very easy to show. G of x is del v by del x by definition. So, del g by del x is by definition that, and this is by, if you simply expand what is going on here, del v by del x and all, it is nothing but that. Right. So, del square by del v del x square actually, right, that will happen to be like this. Obviously, because these conditions are true, that means del square v by del x 1 del x j, this is actually I, okay, del x, okay, right. So, del square v by del x I del x j is equal to del square v by del x j del x I, that is from standard calculus. Okay, this is that I can take the partial derivative in any sequence, that is all it tells you. So, then obviously, my symmetric condition is satisfied actually. Okay. So, the matrix has to be symmetric actually. Okay. Okay. So, if g of x happens to be a gradient function of v of x, then this del g by del x is symmetric, that is what we have shown. Now, what about the other one? If this matrix is symmetric, then what will happen actually, that is sufficiency actually. So, we assume that this matrix is symmetric, okay, that is del g I by del x j equal to del g j by del x I, and we need to show that this del v by del x I, if I take, there is nothing but the same g I of x, which is gradient vector actually. and for that we can show that this b of x needs to be evaluated that way, we just discussed about that. And then we talk about, okay, let us say del v by del x1, what does that mean actually? Okay. This is entire expression, right, this is a v of x expression. I just take del v by del x1 left hand side. Okay. So, if I take del v by del x1, the first one is contains only x1 by the way, okay. This expression it contains only x1, right. So, it will give me g1 is a function x1, and then all other things it will the partial derivative will be pushed inside actually. So, I will just take that partial derivative inside, so del g2 by del x1, del g3 by del x3 like that actually. So, it will continue that way, and I will be able to show this I mean all that in partial derivative I will take it inside actually. Okay. So, I have got g1 plus a bunch of integrals to evaluate and all that. Okay. Then what happens, if you see this integral to be evaluated and all that actually that way, then it turns out that first one is g1 anyway, second one is g1 of x2 tilde. Okay. Why is that? Because if I see this I will invoke this condition that this is true. Okay. Del g, whenever I have del g1 by del x2, I will consider that as del g2 by del x1, and that is what I will do here. Del g2 by del x1 is nothing but equal to del g1 by del x2, this expression here, because this is already symmetric, that condition I will invoke actually, whatever condition I have here. So, if I invoke that, then evaluate the condition, then what will happen? This is actually del g1 by del x2 and then integrated over del x2, and similarly the last one is del g1 by del xn integrated over del xn. So, that is what will simplify the procedure, that is what is written here. So, from this expression to this expression I have invoked this condition actually. Okay. So, when I invoke this condition I will be able to integrate this integral values also, and that will lead me to some sort of evaluation like that. Everything will happen in terms of g1 only. Okay. And then what these values what I see here is nothing but this expression minus this one, right, I mean evaluated from here to here anyway. So, that way. So, if I see this carefully, what will happen, this one, this g1 of x1 and g1 of x1, this gets cancelled out actually, right, this particular thing is same as this one, positive negative. Okay. Similarly, the other things will also cancel out and you will be left out with only this fellow. Okay. So, that is what we are telling here, we are left out with only g1, that means del v by del x1 is nothing but g1 only. So, similarly, del v by del x2 will be nothing but g2, del v by del x3 will be nothing but g3 like that actually. So, that del v by del xi is nothing but gi. So, that is how we will be able to show both actually. First we showed that, okay, if it is, I mean this is, if this is the gradient vector, then obviously if I take derivative it happens to be a symmetric matrix, very straightforward. The other one is, if it happens to be symmetric, then if I take integral and all that, I will be able to show that this matrix what I started and all that is nothing but the gradient of gradient vector of V actually. I mean, so that is where this if and only if condition happens actually. Okay, so summary part it tells you what actually. Okay, a function g of x is the gradient vector of a scalar function if and only if the matrix is symmetric. That means, you have to select a g of x such that this matrix del g by del x is symmetric, that is all you have to do, and certainly it will lead to a Lyapunov function sort of thing later basically. Okay. So, that is what you need to do here actually. Okay. So, let us see that through an example. Okay. Example is, okay, say this is a small example, x1 dot is like that and x2 dot is like that. So, solely x1 dot x2 dot if you put equal to 0 0, that means the equilibrium point has to be 0, that is the first condition we have to see actually. So, if it is equal to 0, then x1 is 0 and this is equal to 0, then this is already 0, this will be x2 equal to 0, right. We want to see what is an equilibrium point actually, right. So, if we want to see what is an equilibrium point, we put this one 0 and this is also 0, and this will give me that x1 equal to 0, and this will give me that once x1 is 0, this term is not there, that means x2 is 0 actually. So, I got x1 x2 equal to 0 0, I do not have to do any coordinate transformation basically. Okay, so x0 is an equilibrium point actually. Okay, so then this Alright. So, this is now we start with applying this variable gradient method. So, that means we start with del v by del x, let us say g of x, and we assume that we have to select this g of x in such a way that del g by del x has to be symmetric matrix, right. So, if I select something like A times x, del g by del x is nothing but A basically, some matrix A. So, if I take this matrix to be symmetric, then I satisfy that condition, del g by del x is symmetric basically. Okay. So, del g by del x is something like this matrix k times x basically, where this k is nothing but a symmetric matrix. So, I start with this k 1 k 2 and k k off diagonal. So, obviously, it is a symmetric matrix. So, I have to select this k 1 k 2 and k in such a way that I will be able to use some of the Lyapunov theorems actually. My v of x, when I solve for v of x, it will satisfy the first two condition actually. So, we started with del v by del x. So, del v by del x, if I see this is del v by del x is k 1 times x 1 plus k times x 2, and the second component is k times x 1 plus k 2 x 2. So, that is what we start with actually. Okay. So, what I have taken is with this one what I have simplified is I have taken k equal to 0 here already. So, if I take k equal to 0, I have a liberty of selecting whatever I want actually, right. So, I select this not only a symmetric matrix, but simply a diagonal matrix actually, which is also symmetric anyway. So, k is there, with that del v by del x is like that. So, if I integrate this v of x, I mean integrate this del v by del x in the way that we discussed before, that means first 0 to x 1, okay, this integral, then 0 to x 2 along x 2 path, keeping x 1 as a free variable basically. So, then this g 1 is k 1 x 1, so that I will have to integrate, and g 2 is nothing but k 2 x 2, I have to integrate that one actually. Okay. So, if it is I mean then if you very clear that this is like that actually. So, as long as I select k 1 and k 2 as positive constants, then I am done, because v of x is positive definite actually. So, k 1 k 2 positive, and then v of x is positive for all x not equal to 0, and v of 0 is also 0, that is another issue, that you have to land up with an expression for which if I plug in this x equal to 0, then I should get v of x equal to 0 also. Okay. And this one also satisfies, this expression also satisfies that condition, quadratic expression essentially. I mean what we really got is a quadratic expression which will satisfy all the conditions anyway basically. So, choose k 1 k 2 positive, and then v of x is positive for all x not equal to 0. So, v of 0 equal to 0, and certainly v of x is a Lyapunov function candidate actually. Okay. So, then v dot we have to be able to show that, because v dot of x we still have to work out, right. So, I mean the way we selected here, it does not give an impression, but the way we need to select in any practical problem is we first have an eye on this one, whatever system dynamics you have, and based on that we select this, which will also satisfy the symmetric condition and all that actually. Okay. Alright. So, we will worry about v dot now. V dot is that. So, we put that k 1 k 2 and then analyze. So, we will end up with some expression like that. So, nothing can be said more about that unless we know some a b k 1 k 2 all that actually, but v dot ultimately has to be negative definite function, remember that. So, now we choose let us say k 1 k 2 1 here, okay. Then we will end up with some expression like that. Still we cannot say anything more than that until you do some further analysis actually. And what is that further analysis? This expression what you have v dot is nothing but I can write it that way. The same expression what I have, I take negative sign here, okay, then both will be negative and things like that, and then I will be able to write it that way actually. Okay. Alright. So, what does that mean actually here? Okay, and this expression further assumes that this condition is true. If this condition is not true, you cannot write it that way. Okay. So, with the assumption that my original equation what I started with satisfies this a b or I mean this constants a b satisfy this condition, a is greater than 0 and b is negative, a is positive, b is negative, then I will be able to show something like that. And what does it tell you? Now, any expression like this, that means for small x 1 x 2, okay, this expression is going to be positive actually, because this is a positive number after all actually, right. So, I have got some domain around x 1 x 2, okay. If I say x 1 x 2, okay, and this is equilibrium, some small domain is there around 0, for which this b is larger than that domain actually. If I take x 1 x 2 combination in multiply x 1 and x 2 and then multiply, then whatever that is there, then norm b and this modulus of b what I am talking about here is greater than that value. Okay. So, obviously this expression that you see in parenthesis is positive value actually, and once A is positive value, negative of A is negative, and this is also positive, that means negative of that is negative. So, obviously, V dot is negative definite actually. So, that means V dot is less than 0 in some domain D, okay, and it is and that domain what you are talking, the whatever domain also contains equilibrium point actually, that is more important actually. So, this domain what you are talking here, domain D, whatever from this expression whatever you are concluding, this domain encircles the equilibrium point. If it does not encircle, it does not contain that, then also you will fail actually. Okay. So, also remember some of those things actually. Okay. That means V dot of x is negative definite in D, and hence the system is locally asymptotically stable. Okay. So, this example is a small example after all, but using this example we started with some condition like that, where this matrix is symmetric and all that, we started with that. Then on the way we assumed this diagonal matrix, and on the way we assumed this is K1 K2 identity. That means, we simply started with as good as telling that we simply started with del V by del x equal to x1 x2. I mean this x1 and x2 in the second component, that is what we started with. Then carried out with this algebra and then tell okay V of x is like that, and it satisfies the property that V of x wants, but V dot of x when you want to conclude something, we have to further assumptions and all, where you assumed K1 K2 1, and then also assumed that A is positive and V is negative. Under those assumptions, it turns out that V dot is negative in some domain D which contains origin, and hence in that domain at least the system V dot is negative, and hence the system is locally asymptotically stable. Okay. And also there is another concept that we are going to discuss in the next class, or maybe to this class itself or something. V dot is negative in the domain D does not mean that your trajectory starting with this domain, any point in domain D will ultimately go to equilibrium, that is not there. All that it tells you that V dot is negative definite in domain D. I mean does not necessarily mean that if you start at any point in domain D will ultimately go to equilibrium point. So, in other words, this region D that you are talking about is not necessarily the domain of attraction. So, there is a domain of attraction concept which will be a subset of D. Okay. So, we will talk about that later in this class or probably next class or something, I mean probably in this class itself and things like that, we will see that. But the actual domain of attraction, that means if you start with that domain you will ultimately go to the equilibrium and all, is some concept called domain of attraction. It is going to be some sort of a subset of this D, and then it will invoke LaSalle's theorem and all that. It is substantially harder to conclude that domain actually. Okay. So, but remember that the properties that you are talking about is in some domain D which will tell you that the system is locally asymptotically stable, that is all it will tell you. But it does not mean that the entire domain D the system trajectory is attractive, nothing like that. Okay, just remember that actually. All right. Now, okay, that is all about this variable gradient method. What about another method? Okay. This is something called Krasovskii's method, and it is very straightforward in fact actually. Okay. We will not worry about the proof part of it here and all that, but let us see, we just want to understand this actually. Okay. And this is like let us assume the system same x dot equal to f of x, and we construct this A of x matrix the regular way. A of x is del f by del x, which is nothing but the Jacobian matrix. Okay. We construct the same kind of linearization concept sort of thing, but we are not really doing any linearization, we are not linearizing the system dynamics, we are simply evaluating the expression del f by del x. Okay. We are not evaluating it around equilibrium point, nothing actually. Okay. So, we will end up with an A of x which is actually a matrix which is nothing but Jacobian matrix. And this theorem tells us that we construct this A of x, okay, and then you construct this f of x which is another matrix which is nothing but A plus A transpose. Okay. And if this f of x matrix turns out to be negative definite matrix for all x in D, okay, then the equilibrium point is locally asymptotically stable. Okay. Understand the condition? I mean, see, it is actually okay, it comes under a theorem actually, but it also gives you a construction of Lyapunov function, because this associated Lyapunov function turns out to be like that. This V of x is actually f transpose f, where f is the original system dynamics matrix, I mean system dynamics vector function. So, if I start with this f transpose f instead of x transpose x, this gives us a candidate f transpose f actually. f is also a vector, remember that. Okay. But the f transpose f is a Lyapunov function candidate provided this f of x, which is nothing but a plus a transpose, is a negative definite matrix, that is the only condition. So, given any system dynamics, I cannot jump into that, I cannot tell okay, f transpose f is a mainly Lyapunov function candidate. This is a candidate provided this fellow is actually a negative definite matrix function, and that is where it is difficult actually. Because if it happens to be okay, let us say if it happens to be only some sort of a linear functions of f is a linear function and all, then a of x will be some sort of a constant matrix. Then constant matrix I will be able to tell negative definite for all x and all that. The moment it happens to be a function of x, then I have to be very careful in telling that whether it really happens to all x in the domain or not actually, that way. Now, that is where it is difficult, but then this theorem is very handy also in a way. Now, so what does it tell? It tells me that okay, I evaluate a Jacobian matrix and then I construct this a plus a transpose, okay, and this matrix function what I am talking this big f of x has to be a negative definite function for all x which belongs to Dn actually. Okay. Then the equilibrium point is certainly going to be locally asymptotically stable, and the corresponding Lyapunov function is f transpose f actually. Okay. Proof is there, I mean we are not going to discuss the proof part of it, you can see some of the textbooks to see that proof actually. And the same textbook that I mentioned in my previous lecture, they will also contain that actually. So, if D okay, now if D happens to be Rn, okay, that means the entire Rn space, and V of x happens to be radially unbounded. Remember, there is no guarantee because f of x, f transpose f we are talking here actually. So, we are not designing from the we are not selecting it ourselves actually that way. So, there is no guarantee that it will be radially unbounded, but if it happens to be radially unbounded and D happens to be the entire Rn space, then the equilibrium point will be globally asymptotically stable. Okay. So, this is Krasovskii's method, and it is a very powerful thing in the it is a direct way of evaluating and all that actually. Okay. So, let us see this why it is so and all that actually, why this A transpose A comes into picture. It is very straightforward. If my V of x is like this f transpose f, then my V dot it turns out to be f transpose f dot plus f dot transpose f. So, f dot is nothing but del f by del x into x dot, this is f dot, right, f dot is del f by del x into f dot, right, f is a function of x only, right. So, if I talk f dot, there is nothing but del f by del x into x dot. So, that is what I do here, and similar thing I do here in the reverse transpose and all that. Then I will end up with this, when I put this x dot is nothing but f of x, right, x dot is f of x. So, I substitute that x dot is f and x transpose is x dot transpose is f transpose anyway, then I will end up with something like this. So, if I start with V is something like f transpose f, I will end up with V dot something like f transpose f big F times small f, and where big F is defined as A transpose A transpose plus A. So, if f of x this big F is negative definite, then obviously this V dot is also negative definite, because this expression tells me like that actually. Okay. This is a quadratic expression in terms of f actually. So, if big F is negative definite matrix function, then V dot is ultimately a negative definite scalar function. Okay. So, what is it? I mean, so we want to show a negative definiteness of a scalar function, but we are taking the help of negative definiteness of a matrix function. So, that is actually complexity increase, basically increase of complexity in a way. Okay. But anyway, so the theorem tells you if I start with like this, I will end up with some expression like that, and hence if my this f of x is negative definite, then obviously V dot is also negative definite, hence I am done actually. Okay, that way. Okay. So, obviously a thing to note here is the global asymptotic stability of the system is guaranteed by the global version of the Lyapunov's direct method actually. Okay. While the usage of this result is fairly straightforward, its applicability is limited in practice, since this big F of x for many systems do not satisfy the negative definite property. That is what I told in the beginning also. This is actually a nice thing to see in math, but it is complexity amplification actually. Like in other words, you want to show a negative definiteness of a scalar function, but you are taking help of negative definiteness of a matrix function, which is actually amplification of complexity actually. But it so happens that your f of x contains only small expressions of x and all that, then maybe you will be able to do that actually that way. All right. Now, there is a generalized version of that, this Krasovskii's theorem, which tells us like some sort of a Lyapunov equation expression sort of thing will happen here. Let us see that actually. What it tells me is, let me evaluate this a of x del of by del x anyway, and one more sufficiency condition tells me that that origin is asymptotically stable if there exists this two positive definite matrices P and Q such that for all x that is not equal to 0, the matrix this expression, remember that in Lyapunov equation this is equal to 0, but in general it is not equal to 0. So, a of x is a matrix function now, okay. But there exist two PDF matrices P and Q such that this expression is a negative semi definite, okay. Then okay, in that neighborhood D of the origin, then the system is asymptotically stable. And if in addition this D is equal to Rn and this V of x is radially unbounded and things like that, then obviously it will lead to global asymptotical stability condition actually. So, what does that mean actually? So, I am able to relax this negative definite condition what I am demanding here to negative semi definite condition, that is the more important thing actually. Okay. So, and as we know there is negative definite to semi definiteness is lot of simplicity actually. Okay. So, all that it tells us is there has to be, okay, here it told what actually, it simply was very straightforward. You just talk about evaluating this A transpose A, and if it happens well and good, otherwise no actually. But here it tells, okay, wait a second, I can select these two positive definite matrices P and Q such that this expression which has a additional component Q now, an additional P is multiplied and all that. See, originally it is A transpose plus A, that is all. Now, you have A transpose P plus P A plus Q, where P and Q are supposed to be selected by us actually. So, it gives us lot of flexibility, and it tells, okay, f of x need not be negative definite, but it needs to be only negative semi definite, which is another simplification actually. So, that is what the Krasovskii's general theorem and all that, and this V of x earlier this V of x was f transpose f, now this V of x will be f transpose P times f of x. Okay, if you tell that if this okay, now this is actually nice in a way, because if you think that linear time invariant system and all, okay, x dot equal to a x and all that, and then you tell, okay, if this P is kind of let us say identity matrix and all. So, V of x is nothing but x transpose x, okay. But if it is P is positive definite, then it will take P x transpose P x, and that is what we did in linear time invariant systems in last class actually. Okay. So, then it resulted in a Lyapunov equation which is nothing but this expression equal to 0, whatever the Lyapunov equation, this particular expression that we are talking here, that happened to be equal to 0 for LTI systems actually. Okay. So, all these are kind of extensions of that what you already know in a way actually. Okay. Right, and why it is so? Because if I talk about this linear time invariant system, this is my f of x, right, this is my f of x, okay, this A times x. So, what is my del f by del x? Del f by del x is simply A, right. I will end up with simply A basically. So, all these concepts are kind of nicely exploited in that side actually. So, what is the proof part of it? Like if I take V of x is equal to let us say f transpose P f, then V dot is will follow through this algebra, which is very straightforward anyway. We have done it before, but here this time that P matrix will come into picture here, and then f dot you substitute, and again this is like x dot is f actually. So, we will end up with this kind of a thing. Now, you add and subtract a Q matrix, okay, here. You are just doing that additional algebra here. So, you interpret that as, okay, one component is coming from that and one component is that. Okay. Now, if Q happens to be negative definite, then this expression is again negative definite anyway, and hence all that we are demanding for here is that this expression has to be negative semi definite, right. By definition what you are demanding, there exist two positive definite matrices P and Q actually, right. So, if my Q is already positive definite, that means this expression, okay, not this expression by the way, this entire expression this starting from negative sign included, okay, this entire expression. If q is positive definite, then minus f transpose qf is negative definite, and if so, that all that it means is I have to make sure that this entire expression what I see in the left hand side, I mean not left hand side, but left part of it, this part has to be negative semi definite. So, that is what it tells you that okay, this expression has to be simply negative semi definite, right, that is what it tells you actually. Another example, let us analyze the stability behavior of the following system. Again, it is a small example in 2 dimensional and all that. So, del s by del x happens to be like this. Remember, this is no more a simple number basically. If I have a linear system, I would have landed up with a number actually, but if it is a nonlinear system, I have an expression here, and hence this f is a plus a transpose contains an expression basically. Okay. So, I have to make sure that I have to analyze this f and then conclude something about that. So, I carry out with the eigenvalue of f, okay. I will be able to do that, but eigenvalues itself will be a function of x 2. So, this matrix contains an expression of x 2, right. So, eigenvalue will also be a function of x 2 basically. So, I will let us put that eigenvalue I mean this characteristic equations and then try to analyze this. So, this is lambda plus 12 whole square plus lambda plus 12 into that, okay, minus this 4 into 4 is 16 actually, okay. So, put it there and then expand that and then collect the coefficient and things like that. So, lambda 1 2 happens to be like this actually. So, these are functions of x 2 basically, okay. So, you analyze this expression. Now, you try to simplify 2, you cancel out and things like that, whatever simplification is possible here. Then you tell, wait a second, this expression that I have here inside, okay, is certainly going to be in between 0 and this expression 12 plus x x 2 square, okay, because this is something and I am actually taking out something else. But no matter whatever this expression is going to be bigger than that. Okay. So, if this expression is going to be bigger than that, this entire expression is bounded between 0 and that value, okay. And hence what I am telling you, this is plus or minus anyway, right. So, this when you talk about lambda 1 2 is certainly less than equal to 0, okay, for all x 2 in R basically, okay. This is an expression whatever is contained, okay, right. See, if it is negative, it is further reduction. If it is positive, then only there was a chance actually to make it positive and all that. But if it is positive, this expression is never going to superpower this expression, because this expression is less than this fellow anyway, okay. So, if it is less than that, even if I add that quantity, then also I will be landing up with some negative quantity only. So, this lambda 1 2 is guaranteed to be some sort of negative number basically, okay. So, that means A is negative definite in R square actually, okay. I mean no matter whatever is that expression and that quantity and all that. Okay, this A is going to be negative definite actually, okay. So, this is why this V of x, that means I am done with that. This it turns out that I mean using this Krasovskii's theorem and all that, my f which is A plus I transpose turned out to be negative definite, and hence my Lyapunov function is given as f transpose f, which I can evaluate, and this f transpose f satisfies all the conditions that f transpose f if I evaluate at x equal to 0, that means x 1 and x 2 both equal to 0, this V of x is 0. If they are non-zero, this is actually I mean this is like positive quantity. Remember, this some expression whole square plus some expression whole square. So, this is guaranteed to be positive number, okay. So, this expression is positive definite, and this is also radially unbounded. That means, if I increase this negative, I mean this norm, if I go more and more away and away from 0 origin, then this expression is going to be more and more, it goes to infinity actually, okay. So, as norm of x goes to infinity, this expression also goes to infinity basically. That means, it is also radially unbounded. So, what is this essence actually? I landed up with some V of x which is positive definite and which is radially unbounded, and for which my V dot of x is guaranteed to be negative definite. That means, I have this global asymptotical stable condition actually. That means, x equal to 0 happens to be a globally asymptotically stable equilibrium point, okay. So, that is how we kind of I mean use some of these theorems and all that. Now, we can see some of the further concepts. So, this is like construction of Lyapunov functions. Now, how about doing this I mean the other issue. So, what is this what happens when this Lyapunov function we will end up with this V dot is negative semi definite and all that actually, okay. What we do about that? and that is where we need this concept of LaSalle's kind of theorems and all that, before which we want to study what is this invariant set, limit set and things like that actually. Okay. So, let us see what is that thing here. So, what we talk about is like an invariant set. So, a set to be invariant set with respect to some system x dot is f of x if my initial a set M is an invariant set, provided if my initial condition belongs to that set, then for all time my solution will also belong to that set. So, it is obviously invariant, it does not go anywhere else actually that way. So, what is the example? Obviously, an equilibrium point is an invariant set. If I start on the equilibrium, I will stay on the equilibrium always. My solution trajectory is also an invariant set. So, if I start with any point on the trajectory, I will go on the trajectory only. So, if I take all the points in the trajectory and define a set, okay, then obviously that set is invariant actually. Okay, I start with any point on the trajectory and I will keep on staying on the trajectory actually. Then obviously, a limit cycle is also an invariant set. Again, also limit cycle is a cycle in the state space, in the closed curve in the state space. Okay. So, that means if I start, this is a closed curve, let us say, if I start any point on the limit cycle, then I will keep on moving on the limit cycle actually. And then there is this another example which tells us that okay, if I define omega L such a way that V of x is less than equal to some number L, okay, some positive number L, where V of x is a continuously differentiable function such that V dot x is less than equal to 0 along the solution of that, okay, then this set is also invariant. And why this definition? Because this definition is what we are going to use it in LaSalle's theorem in domain of attraction and all that actually. Okay. So, whereas these examples are very intuitive, but this example is very useful actually. Okay. So, we define a set which is like x belongs to R n where V of x is less than equal to L, that means this defines some sort of a level set actually. If V of x is equal to L, then that will define a set which is a level set, but we will define V of x is less than equal to L. So, that is an entire domain sort of thing. Within that domain V of x is continuously differentiable such that V dot of x is also negative, less than equal to 0 along the solution. Okay. So, just remember that set is also an invariant set actually. Okay. So, condition this condition what it means, if we start with that and that V dot is less than equal to 0, that means I will never be able to come out of this set actually if I define some sort of a number here, because V dot is negative anyway, right. So, I started with some positive number, but V will keep on decreasing. So, I will never be able to come out of that set basically. So, that is the meaning actually. Now, what is limit set? Limit set tells us that the dynamic system x dot f of x, okay, this is a definition, any big definition anyways. Let x of t be a trajectory of the dynamical system x dot equal to f of x. Then the set n is called the limit set or positive limit set of x of t if for any p that belongs to the set n there is a sequence of limits t n, okay, this curly bracket is a sequence actually. Okay, and then sequence of time actually, right, t0, t1, t2, t3 and all that. So, for any point p that belongs to n, there exists a time sequence tn 0 to infinity such that ultimately my x of tn will approach this point p actually. Okay. When tn goes to infinity, then my x of tn should go to this point p actually. Okay. So, that means roughly speaking the limit set n of x t is whatever this x of t finally goes actually. X of t will go somewhere, right, obviously. So, wherever it goes, that is actually the limit set actually. Okay. It may go to equilibrium point, it may go to a limit cycle also. Okay. If it is a limit cycle, it is actually infinite points actually, right, on the limit cycle. So, roughly speaking that n the limit set actually is a set of points that wherever this x of t tends to in the limit actually, when t goes to infinity it will go somewhere, that is the set actually. Okay. Right, and an example obviously an asymptotically stable equilibrium point is the limit set of any solution starting from a closed neighborhood of the equilibrium point, right, by definition. If it is asymptotically stable equilibrium point, obviously the trajectory is going to go to that equilibrium point anyway. So, obviously in the limit the solution will converge to the limit point actually or the equilibrium point, hence equilibrium point is a limit set actually. But that equilibrium point must be an asymptotically stable equilibrium point, otherwise you cannot tell that, because the solution may not converge to that otherwise. Okay, if it is unstable equilibrium point, it does not make any sense actually, because it will not have any, I mean probably if you consider only that equilibrium point as a set, probably it is okay, but any domain around that will not satisfy that actually. Okay. Also, as I told, the stable limit cycle is also a limit set, because if is the concept of stability of limit cycle is also there. That means, if I consider this limit cycle, okay, okay, this is a limit cycle, let us say, and this keeps on moving around that. So, if I have some domain around that limit cycle, okay, and in that domain, let us say if I start with some initial condition in that domain, then ultimately my solution converges to that. Okay, that concept is called the stability of the limit cycle actually. Either in some neighborhood of the limit cycle, my solution will converge to that limit cycle actually. Okay. So, if that happens, that means stable limit cycle is also a limit set actually. Okay. So, this is actually a very useful theorem. Okay. It is actually like a subset of what we will study as LaSalle's theorem actually. Okay. This theorem tells us that okay, this V of x is positive definite, a regular condition like that, but V dot of x negative semi definite. Okay, that is what is the utility comes actually. Okay. Let V of x is a positive definite function in domain D. B dot of x is a negative semi definite function in a bounded region which is a subset of D. Okay. And this B dot of x does not vanish, that means B dot of x is not equal to 0 along any other trajectory in R other than the null solution x0, x equal to 0. That is a critical condition actually. So, V dot is negative semi definite, it is okay, fine, but V dot of x is not equal to 0 anywhere else other than x equal to 0. Okay. So, using that additional condition, we will be able to show asymptotic stability in many cases actually. Now, that is where it becomes powerful theorem actually. Okay. And if the above conditions hold good for R equal to Rn, okay, for the entire subspace and all that actually, and then it I mean this region R what you are talking about, okay, this region R happens to be Rn, and then V of x is radially unbounded, obviously you will end up with this global asymptotically stable condition also basically. So, this theorem is actually a very powerful theorem, because many times where you are stuck otherwise that V dot is negative semi definite, you will be able to close the chapter and tell okay, even if it is negative semi definite, V dot of x happens to be 0 only at 0, x equal 0, and hence using this theorem the system is still asymptotically stable. And let us see that same example that we discussed last class. This is that pendulum with friction, and we started with this Lyapunov function, so kinetic energy plus potential energy, landed up with a condition for which this V dot of x was negative semi definite. What about next? Now, we have to analyze what happens to V dot of x equal to 0, whether it remains 0 only at equilibrium point or it happens anywhere else also. So, now for that we need to study it. So, let us study V dot of x equal to 0 for all time, that is the condition that we want to study, when it will happen actually. Now, V dot of x equal to 0 for all time means, if I see this V dot expression, that means x2 this expression has to be equal to 0 for all time, that means x2 equal to 0 for all time. Now, if x2 equal to 0 for all time, then x2 dot is also equal to 0 for all time. Now, I will go back to x2 dot expression, and x2 dot expression is this one now. Okay. That means, using this condition here, I will be able to tell that okay, this happens to be 0 for all time. Now, if this happens to be 0 for all time, this expression, now x2 is 0 already basically, right. So, if x2 is 0 already, then sin of x1 is 0, and sin of x1 is 0, that means x1 is 0 in that domain actually. The only solution is x1 equal to 0 in the domain. So, if as long as I start with the domain, remember it is an open set, the equal to that bound, that means the vertical equilibrium condition is ruled out actually. Okay, if it is closed set, then I will end up with vertically inverted pendulum actually, vertical inverted position equilibrium point, that I am not including here. But any other point around that, if the entire region, the only solution for which V dot is equal to 0 is the equilibrium point that I talked about. Okay. So, that means there exists a region R for which V dot is actually equal to 0 only on the equilibrium point, nowhere else actually. Okay. So, using this theorem that we just talked, that means v dot of x does not vanish along any other trajectory other than the null solution x equal to 0, and using this theorem we will be able to tell that this system, this x equal to 0 is asymptotically stable. So, that is what you are able to do that actually. So, you ended up with v dot is negative semi definite, but we exploited that, analyze that a little further and tell okay, v dot is equal to 0, where is it equal to 0 really, okay. And if it remains 0 for all time, v dot of 0, then it will remain 0 for all time only at the equilibrium point, nowhere else actually. Okay. So, there is a region for which this condition holds good, and hence using this theorem, which is a subset of LaSalle's theorem, we will be able to show that this system is still asymptotically stable. And now we are happy because we know that is reality, right. In the pendulum with friction is supposed to go to 0 ultimately actually. So, that is that is how we will be able to show that. How about example 2? Let us talk about another example, x1 dot is x2, x2 dot is that and things like that. So, v of x is actually alpha x1 square plus alpha 2 x2 square, where alpha is greater than 0. Then v dot of x is del v by del x transpose times f of x, and then tell okay, take you through this algebra and all that, because f1 and f2 are available, you put it there, and then you tell okay, this is my expression actually. Okay. So, v dot if I analyze, that happens to be like that. Again unfortunately, this is actually negative semi definite, it is not negative definite, because this expression, if it is 1 were not there, this 1 is not there, then I will be able to show that. But if this 1 plus expression creates a problem here actually, it does not tell that means negative definite, but it is certainly negative semi definite. So, that is what I am telling, many of the times you will be able to show that is negative semi definite, but negative definite you will not be able to. No, so what I mean, we will consider the same condition that v dot is equal to 0 for all time, then it tells me that if v dot is this expression anyway. So, this is never 0, because 1 plus some expression is never 0. So, that means x2 dot, I mean x2 has to be 0 for all time, that means x2 dot is also 0 for all time, that x2 dot is 0 means this is x2 dot expression. So, this expression has to be 0, but x2 is already 0. So, wherever x2 is there I will take out, and that will give me, say this is 0, x2 is 0 already, right. So, that is 0 and this is also 0. Okay. So, what is left out? Left out is only that. So, that means x1 is also 0. So, that means x equal to 0 actually. Okay. We are able to show that v dot is 0, v dot of x is 0 only on the equilibrium point, nowhere else actually. Okay. So, that is how we are able to conclude using that theorem that this equilibrium point what you are talking is still an asymptotically stable equilibrium point. Okay. So, what we have shown that v dot of x does not vanish along any trajectory other than x equal to 0, v dot is negative semi definite, and v of x happens to be radially unbounded also actually, right. This v of x what you are talking is certainly radially unbounded, it is a quadratic function after all for alpha greater than 0. So, it is radially unbounded. So, certainly the origin is globally asymptotically stable basically. Now, finally, the full LaSalle's theorem, okay, the full LaSalle's the original LaSalle's theorem is much more than that, and it actually defines some sort of this set I mean this it defines another set actually. Let us see that in brief, that let us say m, I mean this b which is defined from d to r is continuously differentiable. See all that, remember this b of x that you are demanding here in LaSalle's theorem is all that it needs to be continuously differentiable. Okay, positive definite functions happens to be continuously differentiable, but that is okay. But it all that when that v of x is and hence the I mean what you are talking here is this v need not be a Lyapunov function, it is a function which is continuously differentiable. And these 4 conditions are valid, that means M which is a subset of D is a compact set, and compact set by definition is closed and bounded actually. Set has to be closed as well as bounded actually. So, that M is a compact set which is invariant set with respect to the solution actually. So, that means either it is like something like a equilibrium point, something like a limit cycle, something like a solution trajectory or some whatever thing we discussed before, it has to be one of that. Then v dot is negative semi definite in that particular set, and then we will define a set E, okay, for which this v dot is equal to 0. Okay. All these things we have, whatever examples we studied, all that will satisfy that basically. Okay. So, if you want to see examples, you can go back and see these examples carefully and try to have a meaning yourself actually. Okay. So, that is what it tells us actually. So, D belongs I mean this B dot is negative semi definite in M, and then this define another set E will that way, that means x belongs to M such that V dot S is equal to 0, and then this that means this E is a set of all points of M for which B dot is equal to 0, that is what it means. Then you tell another set which is actually a largest invariant set in E. Okay. So, you have to talk about several definitions and notations here actually. So, you define like M okay, which is a subset of D is a compact set invariant with respect to solution of the system. V dot is less than equal to in that set less than equal to 0 in that set M. Then you define a set E for which V dot is equal to 0, not less than equal to 0, but equal to 0. So, obviously, E is a subset of M, and then you define another set N which is largest invariant set in E, that means N is a subset of E. So, ultimately you will be able to tell that every solution that starts in that domain M, starting in set M, will ultimately converge to N. Okay, that is what the theorem tells actually as N approaches to infinity. Okay. So, what it means actually is if I start with any set M which is defined something like that way, then I will be able to go to N basically. So, it is a subset like that, ultimately I have some subset for which the solution will eventually go actually. And all this theorem, that is what we discuss as a subset of this theorem, I mean this subset of LaSalle's invariance theorem and all that is will satisfy all that actually, but this is with respect to an equilibrium point only, but that is with respect to an invariant set, and hence it is much more general, and this generality is written, I mean these remarks are like that V of x is required to be only continuously differentiable, it need not be positive definite. Okay. And LaSalle's theorem applies not only to equilibrium point, but it also is very much general, and it can be studied for something like stability behavior of limit cycles as well. Okay. So, the earlier theorems I mean that asymptotic stability can be derived as a corollary of this theorem actually. Okay. This is the theorem that we discussed. Okay. It is actually like the earlier theorem that we discussed can be derived as a corollary, very straightforward corollary rather actually. If you simply define these sets and N happens to be the equilibrium point ultimately actually. Okay. So, it will happen to be like that. Anyway, with this thing I think we will stop here in this class, and we will see this, study this theorem once again and see some examples, and then proceed further to exploit this in something called domain of attraction with some examples and all that later, next class probably. Thanks a lot.